Imagine the high-tech, high-stakes environment of a modern gastroenterology suite.
Oh, yeah. It's intense.
Right. Like, picture it. You or a loved one are going in for an endoscopy or a colonoscopy. The room is just dominated by these glowing, high-definition
And
monitors.
huge screens everywhere.
Exactly. Sophisticated fiber optic endoscopes, specialized lighting arrays, and all this complex machinery humming away, keeping track of vital signs and, maintaining vacuum pressure.
It feels like a spaceship.
It really does. It feels like the absolute pinnacle of modern computerized medical science. But the reality of what actually happens in that room, what makes the procedure work, it relies heavily on something far more analog.
It's a really striking contrast when you step back and look at it.
So in this deep dive, we are going to explore the unsung mechanical hero of the gastrointestinal world. We're looking at a super simple piece of equipment and a beautifully deliberate workflow that physically intercepts critical medical specimens before they literally disappear into the abyss.
Because we tend to fixate on the million-dollar optics, right? The advanced imaging algorithms. But the ultimate diagnostic success of the whole procedure often hinges on this completely straightforward, low-tech intervention.
Which is fascinating. And we're pulling today's insights directly from an incredibly detailed, specialized source.
Yes.
We are analyzing a medical training video uploaded to YouTube by Dr. Gadamukala S. Raju.
A fantastic resource.
It really is. The video is titled HCC 147519 Polyp Retrieval Device. It's one of those amazing unfiltered corners of the internet where you get this professional, unvarnished look at the granular mechanics of a procedure room.
It's not glamorous, but it is essential.
Totally. So our mission today is to unpack Dr. Raju's breakdown. We're going to show you how a seemingly minor logistical step, basically managing a tiny plastic trap, is actually the foundational failsafe that makes the entire invasive procedure worthwhile.
Right. And to really appreciate the mechanics shown in that video, we should probably establish the physical reality of the procedure first.
Walk us through it. What's the baseline setup?
Okay, so when the endoscopist locates a polyp, the main objective is to remove it whole so it can be sent for pathological analysis. To do this, they use a tool called a snare.
Which is essentially just a wire loop, right?
Exactly. It's a specialized wire loop that gets deployed through a working catheter inside the scope. And depending on the tissue, they might use a cold snare, which is just pure mechanical cutting force, or a hot snare.
Hot meaning it uses electrocautery.
Yep. It cuts and coagulates at the same time to prevent bleeding. But regardless of which thermal choice they make, the immediate aftermath is exactly the same.
The polyp is cut loose.
Exactly. The specimen is now completely detached and just resting freely inside the gastrointestinal tract, and it needs to be extracted.
And they don't just reach in and grab it with tiny tongs.
No, that would take way too long. They extract it via the scope's biopsy channel using vacuum suction.
And that, right there, introduces the central tension of the entire operation. This is the problem we're talking about today.
It really is.
Because the snare has done its job. The polyp is loose. The physician presses the suction valve, and the specimen is pulled into the biopsy channel at a really high velocity.
It moves fast.
But think about the plumbing of a hospital suction system for a second. High-powered vacuum lines in a surgical setting are fundamentally designed to evacuate bulk fluids, right?
Wash water, biological waste, all of it.
Just clearing the visual field for the camera. So without a deliberate structural intervention, where does that polyp actually go?
That's the terrifying part.
It just rides the vacuum line straight out the umbilical cord of the scope and dumps directly into the main suction canister.
And that main canister is a complete biohazard environment. It is literally a large vat collecting every drop of fluid evacuated during the entire procedure.
Basically a vat of medical waste.
Right. And losing a polyp into that mixture is a massive clinical failure because that tissue is not medical waste.
That's the whole reason you're doing the procedure.
Exactly. It is the definitive diagnostic specimen. Its cellular structure holds all the crucial data about dysplasia or malignancy. It tells you if you have cancer.
So to prevent this catastrophic loss, the clinical workflow introduces the star of our deep dive today.
The polyp retrieval device.
Universally referred to as the polyp trap.
It's such a simple but brilliant tool. It is basically a specialized inline filtration chamber. It's designed to physically intercept the tissue on its journey through the vacuum lines, long before it ever reaches that main waste receptacle.
Dr. Raju's training video lays out the protocol for deploying this trap, and it introduces what I like to call the golden rule of the snare.
Oh, this is a non-negotiable operational standard.
It's treated like a rule of survival. The endoscopy assistant, or the circulating nurse, absolutely must physically insert and connect the polyp trap into the suction line well before the resection ever takes place.
The timeline is critical here, and it speaks to a much broader principle of workflow design and cognitive load management in medicine. Well, think about an invasive procedure. The clinical team is managing multiple variables simultaneously: patient vitals, sedation levels, visual navigation on the monitors.
There's a lot happening at once.
A lot. You simply cannot rely on an assistant remembering to hook up a plastic trap in the chaotic 3 seconds after a polyp is cut and is actively traveling down the suction tube.
Human reaction time under pressure just introduces an unacceptable margin of error.
Exactly. So the video highlights a specific, brilliant protocol to eliminate this variable entirely. It's a forced function.
This was my favorite part of the source material, the aha moment. The video explicitly directs the assistant to have the polyp trap fully integrated into the suction line before they even place the snare handle into the endoscopist's hand.
That physical dynamic is a masterclass in medical teamwork and error prevention.
The doctor might be the one executing the procedure, doing the cutting, but the assistant essentially controls the ignition switch.
Right. By purposefully withholding the cutting instrument until the collection system is verified and active, the team eliminates the risk of the physician moving ahead of the logistical support.
It creates a hard structural pause in the workflow.
And in safety engineering, this is a classic forcing function. It's a design element that prevents a user from taking an action without completing a prerequisite step.
Like how you can't start a car without putting your foot on the brake.
Perfect analogy. Applied to the endoscopy suite, it guarantees that the tissue goes directly into the filtration chamber rather than the waste vat. It removes the burden of memory from the equation and replaces it with a mechanical barrier.
It's so smart. But moving past just a single extraction, we know that the procedure rarely involves just one specimen, right?
Unfortunately, yes. Patients frequently present with multiple polyps scattered throughout the colon.
And the equipment has evolved to match this reality. Because these traps aren't just single chambers. I mean, single chamber traps exist, but the standard device highlighted in the video is a multi-chamber trap.
It's built somewhat like the cylinder of a revolver.
Yeah, featuring multiple distinct filtration compartments housed within a single unit.
The efficiency of that multi-chamber design is critical for maintaining the flow of the procedure, because every time you disconnect a suction line to swap out a single trap, you lose vacuum pressure.
And that's bad.
Very bad. Losing pressure can affect the insufflation of the colon, which messes with the physician's visual field. You want to keep the system sealed as much as possible.
So with the multi-chamber design, the workflow stays continuous.
Exactly.
Right.
Once a polyp is suctioned and visually confirmed to be caught in the active chamber, the assistant merely rotates the outer dial of the trap.
Just click, and you're on to the next one.
Right. It isolates the captured specimen and rotates a fresh, empty filtration chamber into the active vacuum path, instantly resetting the system for the next resection.
It functions with the precision of a highly trained pit stop crew. The endoscopist gets to maintain their focus on the monitors and the tissue without enduring these long logistical delays.
But capturing the polyps in a plastic cylinder is only the first phase.
Right, because once the procedure concludes or the trap is completely full, it has to be disconnected from the vacuum line. And then those specimens are transferred into jars of formalin, which is a preservative.
And the source material spends a significant amount of time detailing this specific transfer. It emphasizes an incredibly strict adherence to precise labeling protocols.
Yeah, standard sequential labeling like Polyp 1 and Polyp 2 is entirely insufficient here.
Completely useless. The video demonstrates that the team is required to map the specimens perfectly to the internal geography of the patient.
Every jar must map to exactly where the polyp came from.
Yes. The labels must indicate the precise anatomical site of origin, for instance, noting that jar A is from the ascending colon, while jar B is from the hepatic flexure.
Now, to someone outside the medical field, that level of detail might seem almost pedantic, until you consider the downstream implications.
The power of context is everything.
The pathologist receiving those jars in the lab is just looking at isolated tissue fragments. They have zero visual context of the patient's colon. If the jars are mixed up or labeled vaguely, that geographical context is permanently lost.
And that geographical context dictates the entire post-procedural care plan for you, the patient. The location of a polyp inside the gastrointestinal tract is a fundamental metric for risk assessment.
A polyp isn't just a polyp.
Exactly. A specific type of lesion found in the right side of the colon carries a vastly different statistical risk profile and requires a totally different surveillance interval than a similar lesion found in the rectum.
So if a pathologist identifies high-grade dysplasia, the gastroenterologist needs to know exactly which section of the colon requires closer monitoring during your next colonoscopy.
Or potentially which section requires surgical intervention.
So precise labeling is just as important for your medical care as catching the polyp itself.
The video insists that the assistant must prearrange and clearly mark these containers because a failure in administrative labeling directly translates to a failure in diagnostic accuracy.
That's intense. All right, so that brings us to the physical limitations of the endoscope's internal plumbing itself.
The obstacle course.
Yes, we've established the standard operating procedure.
Yeah.
Set the trap, deploy the snare, rotate the chamber, and map the geography. It is a highly controlled environment. But biology frequently challenges standardized procedures.
It rarely reads the textbook.
True. The source video addresses a really significant mechanical dilemma. What happens when a polyp is particularly large and fragile? How do you extract it without destroying it in transit?
It's a huge risk. When a polyp is resected, especially with a hot snare, which introduces thermal energy and makes the tissue margins friable, it becomes incredibly delicate.
Friable meaning it crumbles easily.
Yes, very easily damaged. And to understand the risk, you have to visualize the navigational hazard the tissue faces once it enters the suction channel.
It's not just a smooth water slide.
Not at all. It's an intense physical journey. The video traces a rather brutal internal obstacle course. The polyp is first pulled up the entire length of the biopsy channel.
Okay.
It then enters the scope head, where it is subjected to the complex valves behind the suction button.
Sounds rough.
And then finally it reaches the umbilical cord, which requires navigating a sharp, unbanked 90-degree right angle under high vacuum pressure.
Oh, wow. A 90-degree turn at high velocity.
The sheer forces involved in that journey are substantial. Forcing a large, partially coagulated piece of tissue through a 90-degree bend can easily shred it.
So the tissue arrives in the polyp trap as non-diagnostic confetti.
And then the pathologist is unable to assess the margins or the cellular structure accurately.
Which defeats the whole purpose. So, to mitigate this, Dr. Raju's video outlines a specific structural workaround that completely bypasses the internal plumbing. This is the bypass hack.
It's brilliant in its simplicity. Instead of attaching the polyp trap to the standard suction outlet located at the far end of the umbilical cord, which forces the specimen to run the entire length of the machine, the assistant can intervene much earlier.
Where do they attach it?
They can attach the suction line and the trap directly to the biopsy port on the scope head itself.
It's such a smart logistical pivot. By hooking the vacuum directly to the biopsy port, the polyp only travels up the initial channel and is immediately diverted into the trap.
Right. It completely avoids the turbulence of the suction valves and completely skips that destructive 90-degree turn into the umbilical cord.
Preserving the tissue. Now, the video notes this is a specialized tactic, not the standard continuous workflow, but it is a necessary adaptation when preserving the structural integrity of a massive specimen is the highest priority.
It really demonstrates the necessity of clinical adaptability. But, the source material also features another adaptation that addresses an entirely different logistical constraint.
The eco-friendly alternative. This was fascinating to see in a high-tech medical video.
It really was. The modern medical apparatus relies heavily on single-use plastics. The standard multi-chamber trap we talked about is a manufactured plastic component that is utilized once and then discarded as biohazard waste.
But the video presents a remarkably elegant, low-tech alternative that achieves the exact same clinical outcome without the specialized plastic housing.
If a clinic is facing supply chain issues or even just making a concerted effort to reduce medical waste, the assistant can abandon the plastic chamber entirely.
So what do they do?
The video demonstrates a technique where the assistant simply takes a standard piece of woven medical gauze, wraps it securely over the end of the suction canister's tubing, and plugs that gauze-wrapped tube directly into the wall suction outlet.
The physics underlying this workaround are so cool. The hospital's vacuum pressure is pulling air and fluid through the line, right?
Yes.
And the medical gauze just acts as a highly porous makeshift inline net.
Because of the weave of the cotton, the liquid waste and the air pass directly through the gauze unhindered. This maintains the necessary suction pressure at the tip of the endoscope.
But the solid polyp tissue is too large to pass through the weave.
Exactly. It's safely pinned against the gauze by the vacuum pressure.
So the assistant simply disconnects the line, unfurls the gauze, and uses forceps to transfer the captured tissue into the formalin jar.
It achieves the exact same diagnostic preservation using nothing more than a ubiquitous biodegradable piece of cotton and an understanding of fluid dynamics.
It is a perfect example of analog ingenuity solving a problem within a highly digitized environment. I love that.
Which naturally leads us to the consideration of failure states.
The ultimate failsafe, the rescue operation.
Because we've examined the forcing functions, the workflow optimizations, and the low-tech workarounds. But systems, regardless of their design, are ultimately operated by human beings.
Mistakes happen.
They do. And it is crucial to address the specific recovery protocols for when the primary fail-safes are breached.
Right, the catastrophic oops scenario. Let's say, despite the golden rule, the snare was handed over prematurely. The endoscopist was moving quickly and made the resection before the assistant had the suction lines properly routed to the trap.
It's the nightmare scenario.
The vacuum is applied, and the critical diagnostic tissue shoots entirely past the defenses, dumping straight into the main suction canister, the abyss.
The specimen is now floating in liters of collected biohazard waste.
Is all hope lost? What happens in that room?
The psychological pressure in that room spikes instantly. You know, the tissue required for cancer diagnosis has just been lost in the plumbing.
That's terrifying.
But the immense value of Dr. Raju's training material is that it doesn't merely prescribe the ideal workflow, it explicitly details the crisis recovery.
Step by step.
Exactly. And the primary directive in this scenario is strict emotional control. The team does not panic.
You don't just rip the machine apart.
No. They do not halt the procedure, withdraw the scope, or immediately begin dismantling the suction lines to hunt for the tissue.
They wait.
They wait. They maintain the pneumoperitoneum, they maintain the visual feel, and they calmly continue the procedure. The rescue operation is deferred until the clinical work inside the patient is safely concluded.
That takes discipline.
It does. Only after the endoscope is safely withdrawn does the team initiate the recovery protocol. And the mechanics of this rescue are intensely pragmatic.
Walk us through it.
The assistant opens the main vacuum canister, which breaks the sealed pressure system. They then properly configure the polyp trap, attaching it to a fresh suction line.
Right.
The process then becomes an exercise in manual filtration. The assistant utilizes a suction tip to actively vacuum the entirety of the collected waste fluid out of the main canister, pulling it all back through the newly attached polyp trap.
They are essentially using the plastic chamber as a sieve.
Exactly. Running liters of murky biological fluid through the system until the solid polyp tissue is finally caught by the filter.
It sounds tedious and messy, but highly effective. It's like you drop a diamond in a muddy river, so you methodically pump the entire river through a screen until you recover the diamond.
That's exactly what it is. And the presence of this established rescue protocol is what prevents mid-procedure panic. The team knows that even if the primary workflow fails, the specimen is not permanently lost. It simply requires a mechanical filtration phase at the end of the case.
When you synthesize all of these elements from the deep dives, the strict order of operations, the multi-chamber rotations, the geographic labeling protocols, the bypass hacks, and the rescue operations, it fundamentally shifts your perspective on what keeps a medical procedure safe.
It really does. The high-definition cameras and the electrocautery tools are vital, absolutely. But they are ultimately just instruments of observation and action.
Right. The integrity of the procedure, the actual capturing of the data, relies entirely on the structural workflows that manage the physical outputs of those tools.
It paints a vastly different picture of the procedure room.
It really does. So the next time you find yourself navigating the modern healthcare system, surrounded by incredibly intimidating, expensive technology, consider the hidden infrastructure. Behind the glowing monitors and the robotic arms, there is this invisible choreography of safety protocols happening just out of sight.
Entirely dedicated to protecting your vital information.
Exactly. There are teams utilizing force functions, intentionally withholding instruments until pathways are cleared. They're relying on plastic dials and simple cotton gauze to ensure that your specific biological data is perfectly captured and preserved.
It is a deeply reassuring realization. The most critical fail-safes protecting your diagnostic information are not hidden within proprietary software code. They are grounded in fundamental physics, tactile mechanics, and deliberate human communication.
Which leaves us with a really fascinating dynamic to ponder moving forward. We exist in a medical era that is aggressively accelerating toward artificial intelligence diagnostics, automated pathology, and robotic surgical intervention.
We are layering incredibly complex digital systems over our entire healthcare infrastructure.
But it forces you to question, as we build these billion-dollar technological marvels, How many other vital cutting-edge industries are quietly, successfully being held together by the brilliant, undeniable reliability of a simple analog failsafe? Keep questioning the complex systems around you and never overlook the profound impact of the simple solutions hiding in plain sight.